Well, good afternoon. So my name is David Williams and I'm a Professor of Chemistry in the Faculty of Science, Department of Chemistry, University of Auckland. And it's my pleasure to present to you my work on air quality sensor networks. I must apologise that I can't be there in person because I've just had a small plumbing job done on my heart and my doctor tells me it's not a good idea to get on planes just at the moment. And I would love to be there, but I hope that this is satisfactory. So my work is on air quality sensor networks, and I first want to describe to you my background, why I'm able to talk about this. Many years ago I started working on gas sensors, low-cost devices for measuring toxic gases in the atmosphere, and I worked on the material science of these devices, and I was able to help start a venture capital funded company to manufacture and sell these devices. And then I started thinking about, well, what do you do with them? What can you use these things for? Can you do things like measure the atmosphere without using a truck? And I started to develop instruments for measurements of trace gases in air, and particularly at first for ozone in air. And based on that work, I was able to help start a company here in New Zealand called Iroquois, which now manufactures instruments based on my technology. And then I started thinking about networks of instruments and about providing high quality data to people. And so that led to the foundation of another company, again here in New Zealand, focused on sensor networks and their use for the provision of reliable data. So that's what I'm going to talk about today. So air pollution is a big, and it's a shared problem. It's one that is hugely much in the media these days. Everybody cares about air quality, and you have things like the World Health Organization chief saying it's the new tobacco. Well, so where is the conflict that comes in this area? It's a conflicted and contentious area because on the one hand you have the community saying you can't trust the government. You have articles like this in the New York Times and in the Guardian which say the government is measuring in the wrong place, you're not measuring where I am, you might be hiding the data, you're manipulating it, and so this is of course noisy. And the community says, well, we're going to measure ourselves. So then you have on the other side the regulator, the specialists, the government, who say, well, measurements are only as good as the calibration of the instrument used to do the measuring. And the instruments that you are using are complete nonsense. They just produce random noise. So how do you resolve this contention is one of the areas that I've been very particularly interested in from my background of actually developing low-cost air quality measuring instruments. So the key issue here is about the degree of belief in a result. On one level that can be said about what am I prepared to bet on a particular result, and another way of thinking about it is the degree of plausibility. Do I believe this result? And that comes back to the assumptions that are made and their plausibility in the way that the result has been derived. And so these ideas, you need to produce evidence supporting or contradicting the result. And these conflicts, these conflicting constraints imply a need for a fusion of approaches so that you can get data from low-cost devices that are believable, that are plausible. So if we start to address this, we have to think about reliability of data, and so the first thing you have to think about is how do you measure and monitor. And so you realise that there are three elements in this. There's the sensor itself, the thing that produces the data. There's the network, that's the context within which the sensor is deployed, and then there's the system as a whole. And each of these have certain morals about when you think about it. You have to know your device and its foibles. You have to know the purpose of the network and the constraints that applies, and you have to understand the problem domain and what is the information that you require out of this system, and then see if you can put this together in some sort of way. Now, so I first started with a sensor, and I just give you a small example of that. How do the sensors behave in the atmosphere? And the example is a measurement of ozone in the atmosphere using a semiconducting oxide. So the diagram here on the right just shows the signal of heated tungsten oxide in response to traces of ozone in the atmosphere. This is 50 parts per billion. And as you can see, it's a real big signal. There's signal to burn there, so you don't have any problem getting a result, but actually it's slow, and there are failure modes, there are drifts, and so on. So how can you deal with this? And so our first ideas were around checking methodologies that checked for drift of the zero, and methodologies that cancelled out the effects of changes in atmospheric humidity, which are the major constraint on semiconducting oxide sensors. And our solution was to use temperature steps and to use gas flow rate steps, and as a consequence we were able to produce an instrument which was reliable. Now, having done that, we had a device which was this one here, which is a health and safety monitor. And we thought, well, why don't we just try this out as an atmosphere measuring device? So we put it together with some stuff in here, a cell phone modem and batteries and things like that. And then we're able to try this out to see what happened, because the best way to actually find out how your device works is to put it out in the atmosphere and study it. And so our first study was around the Lower Fraser Valley in Vancouver, where we put out 60 devices, and you learn a lot very, very quickly from that. One of the things that we did learn was that the basic device is really very good. It will measure ozone with a standard deviation of plus or minus 6 parts per billion over the atmospherically important range. We found out that it's negligibly dependent on relative humidity changes, and we found out that it's insensitive to the presence of oxides of nitrogen, as is shown in these diagrams, and that work has been published. So then you can improve the device by having more sophisticated inlets, higher quality pumps, temperature controlled enclosures, and so this is a commercial instrument that incorporates all of those ideas, and it gives really excellent results. So here is a device operating alongside reference instruments in a national park in the United States over several months, and it's stable. The devices agree with one another, it's stable and accurate, and it will pick up transients in ozone. Concentration here is transient change from 0 to 30 parts per billion, which happens when the troposphere has a sort of oscillation, and you can see that the sensors track that absolutely reliably. So this is a good device. So now the question is, how do you use this device? And you're going to leave it in the atmosphere. Nobody's going to look at it for a long period of time, because if you do that, that's expensive. So the question is about the drift of the signal. And so how do you know that the results are reliable? Because you can't go out there and calibrate. And so calibration is expensive. So now you have to devise methods for checking and correcting for any calibration drift. And so the method that we developed uses things that happen that you know that are happening. So you know that there are diurnal patterns, you know that there are weekly patterns, you know that there are geographical patterns. And so you can use these patterns to impute reliability for the data. So the way we do it is we develop a hierarchical network. So this is a network which goes from reference standard instruments, of which you have a few, through to well-calibrated sub-reference instruments, of which you have a few more, through to low-cost instruments, of which you have a lot. And what you do is you develop a statistical comparison so that you can transfer the knowledge from the reference stations down to the low-cost stations and get reliable data at high spatial and temporal resolution. So this is an example of that. The first important thing is the definition of the purpose of the network, and we've defined it as a supplement of the regulatory network that extends the regulatory network to neighbourhood scales. And that means that you can reliably determine short-term statistics at local scales. And the diagram here on the left shows one particular example, a sensor that's drifted over time, and this is what's happened to it when we've applied our statistical correction result, and you can see that it's really very good indeed. So you can get data where you can rely on this data, and it goes over well more than 6 months, more than a year now. We've now also extended this into Los Angeles, so we checked that the ideas work over geographically very different areas, and so this is an example again. Ozone. Here is a device on the left which didn't drift over the 7 months of the study. Here is one which did drift, and the red is the first month, blue is the last month. But this method of calibration using statistical comparisons, actually you can see that's the black points there, that really works extremely well, and that has also been published. So what do you get from this low-cost sensor network? Well, you can see here on the left is the reference network, and the numbers marked on here are the reference stations, and the colours show the ozone concentration interpolated between the reference stations. On the right, you see the low-cost sensor network that's been put in, which is a much higher density, and you can now see that there's a much richer information about the variability of ozone. In particular, you can see here that the ozone is very high, not so very far from this station here where the ozone's very low. And actually you can understand that in terms of the way in which oxides of nitrogen, which are generated on the road, running down the middle here, interact with ozone, which is coming down from the troposphere and down the sides of the mountain ranges here. And again, that work has also been published. So plausibility and usefulness now then comes into play. So the data can be accepted because they show something useful. So they reveal some patterns which seem plausible, and the investigation reveals an explanation. And then this may then lead to urban design features that are important for personal exposure. So how does this happen? How can you use this information? You could identify effects on air quality, and you could understand things that you can do in order to improve air quality and to inform people, communities, and policy. So I'm now going to illustrate a couple of examples where that is developed. So the first is to fuse data together, and this is a so-called microscale land use correlation. So what you do is you use diffusion tubes and get a picture of the mean variation with high spatial resolution, and that now gives you a model. And then you use sensors in conjunction with that in order to get the time and space variation at high temporal resolution. And then we also combined it with cameras and things to see where people were, so that you could understand about exposure, which is a different thing. And so you can generate maps like the one on the right there, which show the way the concentration is varying within time and space. And you can then see how you can use this stuff in order to be able to pick out very specific information. So here is an exposure map which shows that how the concentrations are varying with time in the morning, midday, and in the afternoon, because the way the traffic changes in Auckland along this particular street. And the exposure determined by looking at where the people are at particular times is different in the morning than in the afternoon. So this is some way in which you can actually try to use these results. So let's go back over this again. Trusted and reliable air quality data. If you develop a cooperation, as I've illustrated, between the regulators and instrument scientists and people, then you can get resolution in time and space, and you can develop a conversation which depends on the reliability of the models and which involves the people who are making ground observations. And then there are many actions that are possible that are dependent on the timeliness and the spatial resolution of the data, which these methods now allow you to really get with high resolution in both space and time. Here's another example. This is in Los Angeles in the San Bernardino Riverside area, measuring nitrogen dioxide, and it shows the variables that we use to develop a model based on the sensor sites which are shown there, and then it shows where the sensor sites differ from the model. And what does that say? It says, oh, there is something around here, that place there, where there's something that's different. And what is it about that place that's different? Well, it happens to be around a transport hub, and this major transport hub has got lots of trains and trucks and goodness knows what in it. And when the wind is blowing from a particular direction towards the sensor, then is where you see the deviations take place. So the sensor network and the reference network together have produced reliable data that give useful information about the real world that you can do something about. So this is what it is fusion using land use regression as information and being able to pick out things that are important, which alter the way in which people are exposed and what you might be able to do about it. So this is then, how do you use this information to create a better world? That's what this conference is about. And that depends upon the region, the neighbourhood, the people, and how they work together. So I've described to you a set of tools which allow you to measure air quality at high spatial and temporal resolution and be confident about the data. And now, what's the question? This is something that's really interesting. So I've shown you how one can move from assessment to action, and it's a different paradigm to the present paradigm. At the moment, one has dispersed regulatory measurement stations, which are controlled by the government, and there are big actions at supranational scale. Things like putting in ultra-low emission zones, banning diesel vehicles from the city centre, stuff like that, which has a big impact on the community, has a long time to take effect, and creates a lot of conflict because citizens feel disempowered. There's a possible new paradigm, but this new paradigm requires a cooperation to extend the networks to local scale. It requires a cooperation because the tools that I've described are not that simple, so they require specialists to operate them. But what they do in principle is empower communities to assess and change local actions and assess the effects and understand for themselves what are the consequences. So this is different. And so it says to me now, what is the question? How do we use this information now to create a better world? I mean, the answer is in your hands, but it's also a wonderful and interesting new research question. And it's something that I would very much enjoy continuing the conversation about. So thank you very much for listening to me.